Let us start discussion on another topic, that is viscoelastic phenomena or viscoelasticity. We know that viscosity is a property of fluid and elasticity is a property of solid. If we take a stress strain profile, stress represented by sigma, strain represented by epsilon, that means if we take a dumbbell specimen, you have to measure the tensile properties of a material. On application of tensile load, tensile force on the specimen, that gives a profile in stress strain curve like this. On application of stress, deformation increases and gradually it passes through some stage where this linear variation of stress with strain moves towards non-linearity and it passes through some region, comes down, again it may increase and it may fall. So, this is a property of solid. On application of stress, the material deforms. The deformation can be increase in strain for tensile load. There can be deformation, compressive deformation if the load is compressive. Here the stress is proportional to strain up to certain region, which is known as Hooke's region, Hookean region. Means stress is equal to some constant into deformation epsilon. This constant is the proportionality constant, is known as the Young's modulus. E is the Young's modulus. Young's modulus, E is the Young's modulus, and this Young's modulus indicates the elasticity or elastic behavior or elastic response of the solid, which is time. Young's modulus is a time independent parameter. On release of the stress, the specimen reverts back to its original dimension without any permanent change in its dimension and shape. Now, beyond such point, beyond certain limit, it deviates from linearity and deformation occurs in such a way that on release of the stress from any of these points on the stress strain curve, it cannot revert back to the original dimension instantaneously, and it may contain some residual deformation in it, which is called permanent set. So, this is a behavior of a polymeric material which shows deformation up to certain region linearly, proportionally, and beyond which it changes. Such changeover point is known as yield point. Deformation, yield point, deformation at yield, and it shows a plastic deformation. There can be other solids where the stress goes on increasing with strain and ultimately failure occurs. This is perfectly elastic body, and we can say this is a strong material, but it can be brittle also. If the deformation is quite less, if it is stiff like this is a characteristic property of ceramic materials. Metal can behave like this, there can be a necking and then it can fail anywhere after necking, and in that case this portion is not there. This is due to molecular alignment, which is called strain hardening or molecular alignment, or that is due to the decrease of the dimension of this part where necking occurs, and it is a kind of engineering. It can be explained further better with the help of by comparing the engineering stress with the true stress behavior, engineering and true stress behavior. Anyway, what I like to point out that this elastic region is instantaneous and proportional to the stress is proportional to strain, and beyond the elastic region it shows plastic deformation or flow. Now, let us explain why this kind of phenomena occurs in materials like polymers. Polymer is called a viscoelastic material because in polymer we find elastic property of solid and viscous property of fluid. Due to the presence of viscous property of fluid, we find good processability in polymer materials. When we compare polymer materials with other ceramic and metals, we talk about this parameter in favor of polymers as good processability because of the presence of viscous component in the polymer molecule along with elastic component. We can get very good strength properties as well as good processability as compared to metals and ceramics. Let us discuss about that. Now, having the presence of elastic component and viscous component, if there is viscous component, we call that polymer is amorphous. So, amorphous polymers behave like a glass at low temperature, means below certain temperature, say below glass transition temperature Tg, it is rigid glass like material, it can break like a glass. For example, say a vulcanized or a cross-linked ball made of rubber, say rubber ball which shows bouncing property, which is flexible and it shows bouncing characteristics. If that rubber ball is immersed in liquid nitrogen, it becomes very hard, and if it is dropped from hand onto a rigid floor, it breaks into pieces, shatters into pieces. That happens due to the reason that this polymer, the rubber or the ball made of rubber, that goes below its glass transition temperature. Tg of natural rubber is around -72 degrees Celsius, and liquid nitrogen temperature is much below that. So, at that temperature it becomes brittle like glass. So, since natural rubber is amorphous, that amorphous rubber ball in the amorphous rubber in the ball, that becomes glass like and breaks like a glass below this clustering temperature. And this rubber is solid at intermediate temperature above Tg and viscous liquid as the temperature is further raised. So, between Tm melting temperature and Tg at this intermediate temperature, it behaves like a flexible material, soft flexible material, and its property can be explained in this fashion. At small deformation, this mechanical behavior at low temperature of that kind of material may show some elastic behavior, and which can be explained with the help of this equation tau is equal to tau is equal to E into gamma, where tau is applied stress and E is the modulus of elasticity or Young's modulus, and gamma is the axial strain if it is tensile stress applied on the material. And the stress E can be defined as the load divided by area or force divided by area. So, this applied stress for F by A and the constant, which is the modulus of elasticity, and this elongation, which is the is a dimensionless quantity. The change in the length beyond original length divided by the original length, delta L by L0 is the strain. This is a dimensionless quantity. So, stress is proportional to strain up to the elastic limit, and which is time independent. This is the definition of elasticity. So, this component, if in that polymer is solid, this elastic component is present over there, and that component is contributed by a crystalline part of the polymer. Now, if the polymer contains amorphous regions, because a polymer may be considered a semi-crystalline material having such domains of crystallites dispersed in in a flexible matrix like this. So, it can be viewed like this. I mean to say that a polymer chain can start from here having flexible linkage. A certain segment of that polymer molecule may form some crystalline regions or domains. That means, a polymer can pass through flexible region to crystalline region, then flexible region, then crystalline region, then flexible region, then crystalline region, this way. So, in fact, we can have distribution of some crystallites in an amorphous state. This kind of morphology is known as fringed micellar morphology or fringed micellar concept. Now, here these crystalline domains, that means certain segments of the polymer chain enter into form long range order of the that segmental part of the polymer chain, which is crystalline, connected through amorphous regions. So, that crystallite regions dispersed in amorphous region constitute as a whole the viscoelastic material. Now, the viscosity property is contributed by these crystallite zones, and viscosity property is contributed viscosity property is contributed by these flexible zones, and whereas the elastic property is contributed by the crystalline zones, crystalline domains. So, this viscosity property, elasticity property is contributed, can be defined, can be explained with the help of that Hooke's law, whereas amorphous property can be explained with the help of viscosity phenomena. Now, at intermediate temperature, a rubbery solid exhibits the combined mechanical characteristics of these two extremes, the properties of solid and the properties of fluids, properties of liquids. Such type of condition is termed as viscoelasticity. Elastic deformation is instantaneous, as I mentioned, which is independent of time and is totally recovered. Now, let us look into these flow curves. Now, this is the first one, shows an instantaneous load time curve. Here this represents the time of application of load and this represents the time of release of load. So, on application of this load is applied at this time and load is released at this time, and this strain time profile here, you see the strain is increased on application of load, that strain is maintained so long the load is kept over the specimen, load is kept on the specimen, then on release of load the strain is recovered. So, this kind of strain time profile is found in case of elastic body, elastic material, and this is known as elastic deformation, and there is total recovery of the strain which was present at the time of application. That means, the dimension which was initially there in the body, dimension of the body, that dimension is totally recovered on release of the stress. This kind of phenomena, strain time profile, is used to explain the elastic deformation behavior of materials. Now, if the strain behaves in a different fashion, say this is the application of time of application of load. On application of load, there can be some instantaneous deformation, that means some strain is found, some deformation is found on the body. Then slowly with time, on increase of load, strain goes on increasing. Now, when that load is removed from such body, what happens? There can be certain recovery of the strain. Now, here you see this is the instantaneous strain which is parallel to the strain axis without any time lag. This strain was available, then gradually strain increases with time as the load increases, but on release of the stress, now this body is supposed to recover its original dimension, that means supposed to come back to this stage, but it is not, but here it shows some amount of recovery. Then this is the permanent strain which remains, or permanent deformation which remain within the body. Why this happens? That can be explained with the help of the crystalline and amorphous morphology of polymers, or this is a property of polymer having both elastic property of solid here as we see in this case, and viscous property of fluid as we see in this case. So, this kind of deformation is known as plastic deformation, and this happens due to molecular slippage of the molecules one over the other during such deformation, and which cannot be regained. That means, such molecular slippage leads to some permanent change in the material's morphology, whereas in case of elastic body, that permanent slippage occurs, but permanent slippage does not occur. This can be explained if we look into this configuration in a simple fashion. Suppose this is a molecule having such entangled morphology. Okay. Suppose we consider that this is an example of elastic material. Now, if we apply some tensile stress, what happens? This will be elongated, this can be elongated to like a thread, straight thread, an application of tensile stress. Now, such elongations, that means up to this deformation, it is, we can consider that in case of elastic body, elastic system, this is instantaneous, it does not it is not time dependent. Now, stress is released, that means it should come back to this original configuration. So, this is a reversible phenomena. On application of stress, this entanglement is opened, uncoiling, unfolding can happen, and it is straightened. On release of the stress, it reverts back to this original configuration. This kind of phenomenon is known as elastic deformation or elastic behavior. Now, here many other things may be explained, which is found in case of polymer materials. If we find that there is some entanglement, intramolecular entanglement, intramolecular coiling, as well as there can be intermolecular entanglement. So, this is one molecule and this is another molecule. So, this shows an example of entanglement of two molecules. Now, when such tensile load is applied, what can happen in this case? These folded segments can be unfolded. During such unfolding, what happens? Slippage of these segments one over the other occurs. That depends on the extent of deformation, to what extent it is deformed, to what elongation it is stressed. On release of the stress, it may not come back to its original configuration. If there is permanent slippage of, say, this red molecule over this blue molecule, it cannot come back to this original or initial morphology. So, it cannot be reversible. Here, as you have seen, in this case it is reversible, in this case it is irreversible. That happens due to permanent slippage of the molecule as a whole. Now, here in this case, such small deformation to a small extent can unfold a folded segment, but if the amplitude of such deformation is less, it can revert back. In this case, it cannot. That leads to permanent deformation, and here is the phenomena, here is the flow curve, this strain time profile, it leaves behind this permanent deformation. It cannot come back to the original, come back to the zero strain situation. This kind of material is known as leathery material, and which is viscoelastic. The contribution from the elastic part of the material and this contribution from the fluid part or liquid part of the material or viscous part of the material. So, this material is a characteristic of viscoelastic material, and we find such type of behavior in case of leathery material. So, this phenomena is known as time dependent strain phenomena. There can be another situation where again it can have this instantaneous deformation on application of stress. Here in the later part, this deformation with time can be linear with time. In this case, deformation is non-linear. Now, this is not a purely fluid behavior, but due to the presence of this elastic part, it behaves like non-linear deformation, but here this part shows complete property of viscous fluid. On application of stress, strain increases with time in a linear fashion. This is a kind of behavior obtained from rubbery material. So, viscoelastic rubbery material, and this is also a case of time dependent strain. If we look into the viscous behavior or viscosity phenomena of fluid, say liquid, here the strain is not instantaneous. In this case, some instantaneous strain was present, in this case instantaneous strain was present, but in this case no such instantaneous strain is visible here. It is a purely liquid, without having any property of solid, and it shows the deformation on application of stress, and this deformation increases with time, and when that stress is released, the same deformation maintains without any recovery. In this case, you see, due to the presence of this elastic component, there can be a certain amount of recovery due to the presence of elastic component, and strain continues, strain maintains due to the presence of the viscous component, and this is a case of permanent deformation. This is a case of permanent deformation, and this is a case of instantaneous deformation. So, these two are the cases of viscoelastic materials. One is leathery type, one is rubbery type. In this case, it is a purely viscous material, pure liquid material, which shows non-recoverable deformation. So, if a solid is ideal, and if that ideal solid is subjected to a shear stress tau s, then the shear strain gamma s developed due to such shear stress application as a function of the stress applied, that can be represented by tau s is equal to g gamma s. Shear stress, it looks like this. Suppose you can have a stack of playing cards. You can place the stack of playing cards on the board, on the table, and you can suppose this is the stack of playing cards. You put your finger like this, and apply some stress in this direction. So, this way if you do, what will happen? The topmost card will move the farthest distance or maximum distance, and the card below that will move little less distance than that of the topmost card. So, that is a kind of deformation. So, if you consider a material of some imaginary layers, the topmost layer on which the stress is applied, that shear stress is applied this way, that shear stress that causes some deformation on the topmost layer, and the amount of deformation is less on the layer below that. So, this happens due to the frictional force or resistance offered by the bottom layer on the topmost layer. that kind of deformation is known as shear deformation, and the load, the kind of load which is applied or stress applied on that body is known as shear stress. So, this shear stress and shear strain, that is also proportional, and the proportionality constant is G, shear modulus or the modulus of rigidity. When a fixed and constant stress is applied to a liquid or fluid body, it undergoes continuously increasing amount of strain or deformation, which is non-recoverable on withdrawal of stress, as I have explained just before this. A liquid is thus a material of zero yield value, whereas a solid shows a finite yield value. Yield means deformation value, in which the strain is a function of stress as well as time. So, the shear stress tau s applied to a fluid mass, ideal fluid mass that maintained at constant temperature, is linearly and directly proportional to the velocity gradient. So, in case of a fluid mass, if some shear stress is applied, that is proportional to the velocity gradient. As we have seen in case of that shear stress versus shear strain, the proportionality of shear stress versus shear strain, and the proportionality constant is known as shear modulus. In case of a pure ideal fluid, if some shear stress is applied, it is proportional to the velocity gradient dV dr. That means, the velocity gradient, the velocity profile in case of a fluid flowing in a pipe can be also developed, can also be explained, where the velocity of the layer at the center, velocity of the layer at the center of the pipe is maximum, whereas the velocity at the layer adjacent to the wall of the pipe is minimum. So, that gives a concept of velocity gradient, and the proportionality constant in this case is the viscosity, eta is designated by eta, is the coefficient of viscosity, and coefficient of viscosity is again related to another parameter which is phi, known as the fluidity. So, phi is the reciprocal of viscosity or the vice versa. So, eta is 1 by 1 upon phi, and that is equal to tau s by dV dr, and eta is the coefficient of viscosity and phi is the fluidity. The above relationship is known as Newton's law obeyed by Newtonian fluid or ideal fluid. So, from this we understand that a ideal fluid or ideal liquid which follows or obeys this Newton law, where the shear stress is directly proportional to the velocity gradient and the proportionality constant is the coefficient of viscosity, that kind of fluid mass is known as ideal fluid or Newtonian fluid. Also, we can say that this d gamma s shear strain is equal to velocity gradient dV dt. We can also write this way. This is the shear strain rate, we can have d gamma s dt, shear strain rate can be equal to this dV dr velocity gradient. So, we can replace this shear strain rate with the velocity gradient like dV dr, and if we replace that value in that equation of flow equation of Newtonian fluid here, dV dr, if we replace this dV dr with this d gamma s dt, the equation becomes tau s equal to eta into d gamma s dt. This equation states that the shear stress, which is the tangential force per unit area of the surface on which the force acts, that shear stress is required to shear a Newtonian fluid, and that is linearly and directly proportional to the shear strain rate. So, what we have got that shear stress is directly proportional to the shear strain rate. That means, if we want to increase the deformation, rate of deformation of the fluid. So, we have to increase the shear stress, apply the shear stress, we have to increase the stress proportionally, otherwise we cannot make that material deform to a particular extent what we require. This equation is very much useful or can be used to explain the behavior of the polymers during processing and fabrication during compounding. That means, one can have an estimate of energy or mixing power of the machine, mixing machine, power of the motor, that is related to this tau s equal to eta into the strain rate d gamma s dt. That means, how much shear stress is required to have a proper flow characteristic, proper fluidity of the material, say during mixing or compounding of a polymer or a formulation having polymer and different additives, as well as in case of making blend of polymer 1 with polymer 2, etc., etc. How much shear stress is required to obtain a proper fluidity, so that proper mixing is there, proper compound is formed, properly the additives, functional additives during compounding how they are dispersed, or to make a uniform dispersion of the additives, to make a proper mixing of the components to have a compatible or miscible blend. This information is necessary and that can be available. That means, how much stress is to be applied, that can be calculated with the help of this equation. So, a Newtonian fluid being completely devoid of elasticity, which is shows a continuous deformation, as we have seen in this case, this diagram, the viscosity behavior of an ideal liquid, this linear increase of strain with time. So, that Newtonian fluid being completely devoid of elasticity without having any component of solid, that is considered as purely viscous material, and by mechanical analogy its deformation and flow under stress is represented by a weightless piston moving in a cylinder or a dashpot filled with a medium that offers some resistance. The amount of flow, say it can be viewed like this. So, this is a cylinder and dashpot. So, this is the piston like this. So, this piston is weightless. This piston is weightless piston moving in a cylinder or a dashpot. This is the dashpot, this is the piston with a medium that offers some resistance. So, this movement of this piston within this cylinder or dashpot can be compared with the flow behavior of a fluid. The amount of flow gamma s, that is the strain, is a linear function of time. Say gamma s is a linear function of time. So, gamma s is equal to tau s by eta into t, and tau s or tau s into phi into t. Now, this diagram shows the flow curve, flow of a Newtonian fluid with the help of this dashpot piston dashpot model sketch. So, here you see a constant shear stress tau s is applied at T0. On application of stress, deformation increases linearly, and at time T1 that stress tau s is removed. How it can be visualized with the help of piston and this cylinder? Here this is the application of stress where the piston remains at the bottom. It is moved up at time T1. It was at T0 it was at the bottom, at time T1 it is moved up. Now, here by doing so, this piston will get some resistance from this wall of this cylinder, for which that stress tau s is required to move it up from the bottom to take it up, that stress tau s is required, and the slope, that means the ratio of tau s by eta, the viscosity, is the slope. So, this is a flow curve for a Newtonian fluid, or is a strain versus time profile. And if we make a plot of rate of shear stress, rate of shear d gamma s dt, rate of shear is the rate of shear d gamma s dt, means deformation rate of deformation we can say, and this is shear stress. So, shear strain rate, we can say also shear strain rate versus shear stress curve, this is also linear in case of a non-Newtonian fluid, a Newtonian fluid. So, we see that this is the behavior of a Newtonian fluid or an ideal fluid. Now, our polymer materials are non-Newtonian materials, non-Newtonian material or non-Newtonian fluid. Shows a peculiar behavior here. Now, if we make a plot of shear stress versus shear strain rate, now ideal plastic bodies known as Bingham plastic body, if we explain the behavior of such kind of plastic material, what happens on application of stress, there is some instantaneous your deformation you can say, that means this much of stress it can bear without any application of this strain. So, shear strain at the zero shear strain, at the zero shear strain rate, this is the stress value which it can bear, and beyond which it requires increase in stress value with the, that means the variation of shear stress with the shear rate increases linearly. That variation occurs at much higher shear stress. That variation of shear stress with shear strain rate occurs for Bingham plastic, occurs at much higher stress, after which it becomes linear. And there can be other materials which are termed as straight venant body, which does not show any increase of that does not require any increase of shear strain rate. Shear strain rate remains constant at any particular shear stress. These are the two cases, and these are some real situations which we observe with polymer materials. Now, if you look at this curve which is concave downward, this shows a pseudoplastic behavior. Pseudoplastic means it behaves like a plastic, but on application of shear stress, its viscosity decreases. We can bring an analogy to the sand bed on seashore. On seashore, we find there is a sand bed which apparently looks like dry sand bed, but on application of throbbing force with the help of your foot, you will find that slowly water is coming out from the sand bed, although it appears that there is no water. Where from that water has come? Now, there is a property of sand and water that water molecules form an envelope or coating over sand particle that becomes set, that water envelope just remains tightly bound over each and every sand particle when it is under static situation, when there is no load. But on application of pulsating load, what happens? Those water envelope layers breaks and water molecules get released from the sand particle, water comes out and the sand particles appears to be little fluidy, some water comes out, it appears to be fluid. So, that kind of behavior is known as thixotropy. It is a kind of shear thinning phenomena. Shear thinning phenomena means on application of stress, what happens? This viscosity is reduced, viscosity decreases. The decrease of viscosity on application of stress, that means on or increase of shear strain rate, the shear stress on application of shear stress, gradually the requirement of stress decreases. Here you see shear stress decreases gradually with the increase of shear strain rate. So, that kind of behavior is known as thixotropy. This is also this phenomena is also visualized in case of plastic emulsion paint, in which some pigment particles are dispersed in a vehicle. That vehicle is made of some polymer, water soluble polymer and water and some other organic solvents. Their pigments are dispersed, and when it is kept in static condition in a container, that remains almost in a solid like mass. If you open the lid and just make the upside down, the paint does not pour down. That is due to the settling of those pigment particles by these vehicle molecules or the water molecules. Now, on application of stress, what happens? It becomes thin, it becomes the viscosity is reduced, viscosity decreases, and then with the help of brush one can use that paint over wall. The opposite behavior is found in case of dilatant material, which is known as shear thickening. That means, on if you increase the stirring rate of stirring, it thickens, the viscosity gradually increases. So, increase of viscosity with shearing is known as dilatancy property, decrease of viscosity with shearing is known as thixotropic property. And there can be material showing both the behaviors of thixotropy as well as dilatancy, that is known as complex, and if it is purely linear, that is a Newtonian fluid. And that viscoelastic phenomena can be explained with the help of mechanical models. One is Maxwell model, another is Voigt model. This is the Maxwell model, where that elastic component is represented by a spring, where this viscous component is represented by a dashpot. Okay. So, on application of stress, that means some tensile stress is applied, what will happen? This deformation will occur in this A part, this viscous part, and that can be accommodated by that can be accommodated by this spring. The deformation of that deformation can be accommodated by the spring, and this is in series connection, this is in a parallel connection. So, a viscoelastic body is assumed to be composed of an elastic element represented by a steel spring and a viscous element represented by a piston and a dashpot. A simple model is shown below, which combines the pair placed in series Maxwell unit in this case, and another combined in parallel Voigt unit. For a Maxwell unit exemplified by a fiber containing crystalline and amorphous regions, the overall rate of flow combining the contribution of the elastic or viscous elements is represented by this equation. This is the elastic element, this is the viscous element, and the corresponding equation for shear stress tau s is given by this d gamma s dt is equal to 1 by g into d tau s dt plus tau s by eta. On rearrangement of that equation, the flow equation becomes d tau dt is equal to E into d gamma dt minus E by eta into tau, and that is equal to E into d gamma dt minus tau by eta, tau by lambda. Now, here a new parameter has come, this lambda, which is equal to eta by E, is a characteristic constant of the selected material, and that is known as relaxation time. That means some load is applied, then it is released. So, before coming to its original configuration, it should get some minimum time, some minimum time should be allowed, so that slowly that segment is relaxed and it comes back to its tries to come back to its original conformation. That is known as stress relaxation. Now, this stress relaxation on application of an initial stress tau 0 on a viscoelastic material represented by a Maxwell unit, as I have shown in a series combination of spring and a dashpot, the deformation will instantly occur entirely in the spring. Deformation occur in case of entirely on a spring, that is the elastic deformation. If held at a constant strain, there this constant strain, the d gamma dt would be equal to 0, and flow takes place in the viscous element only, okay, and progressive decay of stress takes place. That progressive decay is called relaxation. The residual stress at any time t after application of stress is obtained from this equation tau is equal to tau 0 into e to the power minus t by lambda. This relaxation time lambda is the time over which the stress decays to 1 by E of its original value, that is tau t is equal to tau 0 by E. Now, for a viscoelastic material combining an elastic and a viscous element in parallel, now the stress required to maintain a fixed strain would depend on the rate of the deformation. The stress reaches a constant value as the desired strain is achieved, and thus the system is not associated with a relaxation effect under this condition. By convention, the viscoelastic modulus ER can be computed as the ratio of the stress measured at 10 seconds after straining, designated as tau 10, and the strain gamma. So, ER becomes equal to tau 10 by gamma. The total strain gamma consists of contribution from elastic and viscoelastic deformation. So, this elastic gamma from elastic component and gamma v from the viscous component. So, both elastic and viscous components contributes to the total strain of the body.